Welcome back to EC Fundamentals 1. In this video, we're going to focus on understanding the concepts of voltage and potential and voltage difference or potential difference. These are some very fundamental concepts in this field, and there are some interesting details that we have to pay attention to. So we're going to spend a little bit of time in this video talking about them. The first thing I would like to mention is that in real life, almost everyone comes across the concept of a voltage. Every time you actually try to buy a battery, you're asking the question, how many volts is this battery? Some batteries are at 2 volts, some batteries at 5 volts or 3 volts, and so on and so forth. And of course, there are many other attributes that will come. There are many other issues. For example, you have to consider the volume of the battery or the weight of the battery. But most people, the very first thing they will think about is exactly how many volts. And the reason for that is because there is an interesting connection between voltage and energy, which we will uncover just in the next slide. However, the layperson actually always thinks that the higher the voltage, the more energy or the stronger the battery is. If you ask anyone, if I give you a 1-volt battery and then I give you a 10-volt battery, which one is stronger? Most people will say that the 10-volt battery is stronger and is actually 10 times as strong. In fact, we have battery voltage checkers that are there to do exactly that. You can buy a battery voltage checker and you can connect a battery to it and you can measure exactly how much voltage is there. And interestingly enough, that is a quantity is directly related to how much energy the battery can give you. And in fact, those type of intuitive thoughts are completely correct, but let's find them in a slightly better mathematical way. So let me try to focus your attention back to what we were discussing before in a previous video, where we looked at what happens to a conductor that has free electrons. If this conductor is simply left on a table at room temperature, you will find out, as we have already discussed before, that all you can expect is a random motion of electrons. However, if you do connect some type of a voltage source, like for example a battery, then something interesting happens inside this conductor. And what happens inside this conductor is that there is an electric field that gets established from the high end of the battery to the low end of the battery, and that electric field exerts force on the free electrons. That force is actually equal to Q, the charge of the electrons, times the electric field. And that means, since Q is negative, that this force will be in the opposite direction of the electric field. So all the electrons will basically feel a force that will tend to move them towards the left. And of course, that motion, as we have discussed before, will not be smooth. But what will happen is that on average, you will have a current flow to the right, which means that on average, you will have electron flow to the left. Now, of course, for that type of flow to occur, you need to spend some energy. And this energy is being spent by this voltage source, who is allowing, or rather forcing, those electrons to move. So you can imagine that definitely the more voltage you apply here, the higher the voltage, in other words, of the voltage source, the more current you will have. And in fact, these two quantities will be related linearly for this conductor that you see here. So to make this slightly more precise, we have to start defining first the concept of a voltage difference, and then once this is known, we'll be able to define the concept of a voltage. So the voltage difference really reflects the difference between 2 points in a system, or point 1 as I will call it here, and point 2. So when we talk about voltage difference between 2 points, we're really talking about the amount of energy you have to spend to move a charge from one point to the other, and specifically to move a charge against the established electric field. So if I am looking at moving a charge from point 1 to point 2 against the electric field, so let's say in a more general situation that the electric field might look something like this, and I'm trying to move a charge against this electric field, and this definition, by the way, applies for a positive charge, then I will have to spend some energy. Why? Because this positive charge would basically feel a force that would have been Q times E. And if Q is positive, as is assumed in the definition of a voltage, then this charge will try to move to the left. I am trying to move it against the electric field, so I have to spend some energy. The amount of energy I have to spend to move this charge against the electric field per unit charge is basically nothing else but the voltage. So as you can see very clearly from this definition, if I have to spend more energy per unit charge, then that means that the potential difference between 2 points is higher. Now, as you can imagine from the definition I'm giving you here, V12, which by the way is equal to V1 minus V2, is nothing else but the potential difference between 2 points. In order to talk about absolute potential, which we'll do in a little bit later, we have to know the potential of one of the 2 points. Let me save this for later and right now stay with the voltage difference definition. Now, this voltage difference a lot of times will be given as potential difference. So when we talk about potential or voltage, we really talk about one and the same thing. Most engineers will talk about voltage, while most physicists will talk about potential. Now, as you can imagine, when I just defined the voltage difference, V12, I said this is equal to V1 minus V2. So clearly, I am talking about the difference between 2 points, and therefore I have to be careful about the polarity of the voltage. Here's what I mean. Let's talk about an actual circuit, and let's talk about the device of that circuit. This is this green device that I'm basically marking here. A very common question that people will ask you is, can you calculate or can you measure what is the potential difference V across the terminals of that device? If you're in the lab, the first thing you will do is that you will take a multimeter or a digital multimeter, DMM, as I'm showing it here. You will connect 2 cables to this multimeter, a red one, shown here, and a black one, shown here. And you will take these 2 cables and you actually connect them to the 2 terminals of this device, terminal A and terminal B, or point A and point B. And you will make a measurement. But before I tell you about the value of this, let's just think about exactly what happened when we made this connection. When you take a digital multimeter, one of them will be, one terminal will actually have a negative and the other terminal will have a plus, which basically will tell you that the voltage you will measure will be given the value you see in the digital multimeter, but for the given polarity that you see here. In other words, it is impossible to measure a voltage without assuming a polarity. When you connect the red cable to the plus and the black cable to the minus in the lab, you will basically make an assumption that the point in the red cable is at a higher potential than the point in the black, the negative cable. This may or may not be true, but you're making this assumption when you're conducting the measurement. If the result of your digital multimeter is, let's say, 5 volts, then it simply means that indeed point A is 5 volts higher than point B, which is down here. You don't know exactly what is point A and point B, but you know that the difference between the 2 points is 5 volts, and you also know that point A is higher than point B. On the other hand, if you conduct a measurement exactly as I'm showing it here, but let's say the value now in your multimeter is negative 5 volts, then clearly the result will be exactly the opposite, meaning that now the difference between point A and point B is negative 5. Of course, that would indicate that point B now is 5 volts higher than point A. Now, of course, it is very important to know the polarity of the voltage, as well as it's important to know the value. So same thing as we discussed about the current, here we don't have to deal with the direction of the voltage, but we do have to deal with its polarity. Now you might say, okay, this is what's happening in the lab. What happens when I solve a circuit? So what if I have to solve a circuit here and somebody says, well, here's a circuit that has a bunch of devices. Find me the voltage, let's say, for device A. Even though they may use such imprecise language, find me the voltage of device A, in real life what they really mean is assume a voltage difference between the two terminals of the device A. Let me call this difference VA, and calculate this by assuming a polarity. The polarity I have assumed here inherently shows that this point here, A, is higher than point B. I have to assume a polarity. This may or may not be true. But once I assume this polarity and I solve my circuit, let's say I find that the voltage difference across device A is 3 volts, then indeed it will mean that VA, node A, will be actually the node B plus 3 volts. If the result is different, and let's say that I found that the voltage across device A is -7, then it simply would have meant that the V of node A is basically 7 volts below node B. So it's very critical to understand that polarity does matter, and it happens both when we calculate devices and circuits as well as when we measure them. And simply by connecting the cables in a multimeter, you make an assumption of the polarity, which again, if it ends up being incorrect, you just have to correct for it. Now, what happens if, let's say, 2 different people assume 2 different polarities? Again, nothing bad. For example, let's look at the circuit we have here. We have a very simple device here connected to a 5-volt voltage source or 5-volt battery. Notice, by the way, that the battery has a specific polarity. So the upper terminal of the battery, which is called A here, is 5 volts higher than the bottom of the battery, which is node B. So if somebody says, find me the polarity of a voltage, find me the voltage Vx, 2 different people could have chosen 2 different polarities. The person on the left chose the plus minus. The person on the right chose minus plus. The person on the left, the correct answer for their choice is equal to 5 volts. The person on the right, the correct value for their choice is -5. They both have solved the problem correctly. They both have calculated Vx correctly. Each one of them chose a different polarity, which is fine. This is reflected in the result. Now, let's go back to what we were talking about, differences and absolute values. See, unfortunately, a lot of people, including engineers and physicists, they will use imprecise language, which creates a lot of confusion, particularly in the very beginning. Sometimes they will ask a question correctly. For example, sometimes referring to the voltage V here, they will say, find me the voltage difference or find me the potential difference V. That's the correct way to ask the question. Sometimes, on the other hand, when they refer to this device, they will say, find me the voltage V. And by that, they mean find me this value here, V, with the polarity given there. In other words, it's very important to understand when we talk about potential difference and when we talk about absolute potential. As I said before, unless you already assume an absolute potential at some point in a circuit to be known, then you can't really talk about absolute potentials. You can only talk about potential differences. For example, with the measurement shown here, the potential difference V is 5 volts. On the other hand, if somebody says, you know what, let's assume that the potential at point B is 0. This is something that you can do, and in fact, we often do. In exactly the same way as in mechanical engineering, we may have the ground, and we may assume that the potential at the ground is basically 0, or the energy at the ground is 0, such that we can say that an object that is sitting at the height h has a potential energy of mgh, where h is the height, g is the gravity, and m is its mass. In exactly the same way, we can go ahead in a circuit and assume that at some point in the circuit, the voltage is known and its value is 0. This is usually called ground. Ground may actually be physical ground, which means that literally this point in the circuit, we're going to go ahead and connect it to the earth. We're going to ground it. Or it simply may mean that you have assumed that at that point the voltage is 0, which is something, as I said before, that is not only allowed to do, but we are encouraged to do. In fact, the convention in all the circuits we're going to be seeing later on in this class is that typically the bottom layer of the circuit will be assumed to have a 0 potential, and everything else will be referred to this potential. So with the assumption that VB is equal to 0, we can basically say that VA, which is nothing else but V minus VB, is going to be equal to 0 volts. So thank you for staying with me with this video, and we will be back next time.